No, I said we'll start right at 1, but we're going to give a few more minutes for people to trickle back into the room here at ARB in Sacramento. So please be patient for a few minutes, and we'll get started soon, though. Thank you. All right, so good afternoon, and thank you for logging back on to the afternoon session if you were here also in the morning. We're going to go ahead and get started. Just as a reminder for people on the webinar, we are using the phone line for audio, so if you're logged in using VoIP on your computer, please choose the phone line option and dial in with your phone line to be able to ask questions throughout the presentation. And then for people in the room, if you didn't sign in, could you please sign in on the sign-in sheet when you get a chance. And then just like this morning, we are going to try to moderate the questions just to keep the flow going. We will try to answer everybody's questions as well as we can, but we're probably going to take questions in groups. So we'll go through different sections, and then once we finish a section, there's probably a break, or there are breaks throughout the presentation. And once we get to those breaks, we'll look for or go to questions online and in the room. And if questions kind of pile up, we'll take breaks more often for questions. So I guess with that, we'll go ahead and get started. This morning's presentation was an overview more of fundamental ideas and principles related to GIS and basics about doing a spatial analysis in ArcGIS in particular. So this afternoon is actually going to be dedicated to the analysis we performed and the tool that we developed that we are calling CHIT, the California Hydrogen Infrastructure Tool. So this is the purpose of this afternoon's discussion is really to provide the detailed review of the methods, the data sources, and the considerations that really guided the development of this tool. We're going to discuss the motivations, how those motivations translated into the actions and the choices that we made, assumptions that we made in the tool, and also to provide a public vetting process or opportunity for this tool. So like I mentioned today or earlier, we're going to try to get to every question we can, but we're definitely aware that some of this information takes time to process and time to consider. Definitely invite feedback later on as you might have a chance to consider the information presented today. And we will be making these slides available in the future as well as a recording of this webinar, both the morning and the afternoon session. So again, like this morning, we'll provide a high-level overview of the motivation as it's related to AB8. We'll discuss the guiding principles that really sets the framework for a lot of the decisions in our work. And then we'll just start discussing all the different factors that went into this analysis. So how we got to a roadway and travel speed data set, coverage, how we estimated coverage, other data sources that maybe we didn't end up integrating in the final version, like traffic volume, and then looking at how we assess the first adopter market. And then you can see that our last two points are actually open discussion related to how to share this model, how to share the output results, and future development for this tool. So in this afternoon session, really, we're going to, hopefully you'll be able to get some of these questions answered, like what was the traffic-related information that we used, how did we use it, what wasn't used, why not, what was the algorithm for, how did we calculate coverage, how do different financial indicators of the potential first adopter market, how are they actually assessed in this tool, and how does the tool determine the relative priorities of different areas, and how does it actually identify those areas? In particular, the priority areas that you saw in the AB8 report, and then in the CEC draft solicitation concept. And then, of course, what are the current plans for further development? And that's more of an open discussion. So as introduction and review, ARB through AB8 is legislatively required every year to assess the plans for fuel cell vehicle deployment and the status of the hydrogen infrastructure and where new hydrogen infrastructure needs to be placed for future funding opportunities. And so we accomplished this with two different tools. The first is CHAT. We developed that first in support of our 2014 June AB8 report, and that tool relies mostly on the surveys that we distribute to the OEMs annually. And we developed essentially it as a database tool to be able to track the responses to that and then perform some calculations to determine what that means for the future on-the-road vehicle population in terms of fuel cell vehicles. This year we then developed CHIT, which is a GIS tool that allows us to consider more information than just the survey. It allows us to look at what the potential market might be. It allows us to spatially assess what coverage might be like with the existing stations in state and look at the difference between the market and that coverage and make recommendations for the report. And then, as you saw, if you attended or read the draft solicitation concepts or attended CEC's workshop in August, that some of these concepts, of course, and some of these recommendations were included there. And so this is all part of the AB8 process. So what is the big picture? What are we really trying to do with this tool? Well, it's to plan infrastructure placement appropriately for the upcoming fuel cell vehicle releases. So to do that, there's three main steps. First, you need to identify the market. In reality, there are both close to home markets, main your main large retail markets, but then there can be perhaps destination or connector station markets. Just out from the beginning of this, I want to point out that the CHIT tool is made to analyze the more close to home, the first adopters market, their convenience market, their everyday daily routes that we're looking to satisfy. Once you've identified the market, you then need to evaluate the current infrastructure and determine how much does the current infrastructure actually meet that market, and then simply identify what are the biggest gaps then that are left over. And so we do want to provide some way of looking at these different areas and providing some measure of importance or some relative priority for those areas. And more importantly, we want to do this year to year. AB8 is, of course, a multi-year program, and so we're going to need to do this analysis continually as the years go on. So each year that solution might change. The relative importance of different areas might alter based on new stations being built or new information that we get from stakeholders. And so CHIT is a planning tool intended to provide general direction for needed infrastructure. It is not an optimization tool. It is not meant to tell you exactly what street corner a station needs to be on, but it's to provide general areas where applications might be most successful for new infrastructure. And it evaluates the relative need for hydrogen infrastructure based on this gap analysis between the market and the existing coverage. So on the bottom here, we have a quick example of a couple of cities, City A and City B. City B, even though it has smaller coverage provided by existing stations, its market is also smaller. So when we compare the coverage and the market between City A and City B and look at that gap, we can see that even though City A has a higher coverage already, its market is so large that it still is the highest priority. And we do see this in the output results. And so that's really the type of assessment we want to make. We don't want to simply say just because an area is covered, it's done. It has to have coverage that matches its market. And so this coverage idea is a central theme in our analysis. It's a central theme throughout the entire process. And coverage can be considered to be sort of the conceptual representation of convenient access to fueling stations. It's often discussed in terms of drive time. Sometimes it's discussed in terms of distance, but we are discussing in terms of drive time for this tool. So for example, you can consider coverage is provided to all neighborhoods within a 6-minute drive of a station. So over here on the right of this slide, this is just a rough coverage estimate of the San Diego station that's currently being built. And it's different drive times. The 6-minute drive time is kind of that green color, but it goes all the way out to 15 minutes at the red color. Now, coverage can be conceptualized as binary, essentially yes or no. A neighborhood is covered or it's not. Or it can actually be conceptualized as degrees of coverage, different drive times from different stations can mean a different amount of coverage for a certain area. You might consider it more convenient to be 10 minutes away from a gas station than to be 20 minutes away from a gas station, for example. So we are looking to incorporate those kinds of metrics. And we're working within the mindset that well-planned coverage increases consumer confidence and adoption of the vehicles, fuel cell vehicles. This is kind of an example from some early investigations we did, looking again at the San Diego station, where you can see how service areas evolve throughout the day. And this is all based on traffic. So as traffic gets worse, you can't go as far in a given amount of time, and so service areas shrink. And so to kind of freeze frame a couple of frames from that, if we look at 12 a.m., so probably zero traffic on the road, we can see the extent of service areas, how far you can get within 15 minutes from that station. And then at 5 p.m., during the peak traffic in this data set, you can see how much that area of coverage actually shrinks. And that area shrinking has an effect on the population that you've actually provided service to, right? It's not an overly complex concept, but it is something that can be quantified. So if we actually look at different drive times and the amount of population covered within those different drive times, we can see there's a major effect. Between times of no traffic and peak traffic, you can lose service to 1/3 to 1/2 of the population that's actually covered when there's no traffic. So it's an observable, quantifiable relationship between coverage and traffic patterns. And this effect of this relationship, of course, varies with the time of day because of the traffic patterns and the different speeds at different times. Time varying analyses are interesting. We did look into this for a long time, but you do not necessarily need to analyze every hour and every minute of the day in order to do the planning that we are looking at. We are looking at trying to plan essentially for a worst case scenario for your peak traffic time. So if you plan for a peak traffic time, a PM peak, that can allow you to do that. So we have gone forward with that, that assumption. So Leslie, do we have any questions online yet?
That's something.
Okay. So moving from there, we want to discuss the guiding principles of the development of this tool. So CHIT is envisioned to be a tool that can be used year after year for public planning and reporting purposes. It can provide a consistent assessment across the entire state. We had a question earlier this morning about information that's more targeted to particular areas and how we try to avoid that specifically in this analysis because we're looking for a baseline analysis that can be fairly performed across the entire state. Because of these motivations, there's a number of principles to keep in mind, and that if you kind of keep these in the back of your mind as we're going through these next slides, you'll see that it makes sense why we did what we did. So the first is CHIT is a relative assessment. So when we're planning for our priorities, the total coverage and the total need and the total number of vehicles might change from year to year, but as those change, the relative importance of those changes is really what you want to focus on. You want to focus on, the areas that have the highest need as the years progress, and what that level is may change. So your highest need in 2005 may be different, or 2020 may be different from today, but the relative assessment is really what gets you to those priority stations. Those outliers is what you're really trying to find. CHIT is a statewide assessment, so again, while individual site assessment can account for special considerations, a lot more information, a lot more detail, broad statewide planning needs to be free of these area-specific special considerations in order to have a consistent basis. We are really looking for an analysis that has a consistent basis, and our data sources therefore have to be able to meet that. They have to be as equally viable across the state as we can possibly implement. In its current version, CHIT only assesses the first adopter market. So participants in this first adopter fuel cell market will evolve over time. In the full market will evolve over time, but right now we're in the first adopter phase, and those first adopters are assumed to share certain characteristics. Principle number 4 is that identification of that market can be estimated by considering relative distribution of multiple demographic indicators. Okay, so we don't necessarily look to find every house that has a certain income with a certain number of vehicles and a certain educational attainment. What we're doing is we're looking at areas where these, on average, or where the distribution of these values are higher than in other areas. And we're saying that where these overlap, where these hotspots overlap, that's really where your market is going to be. And this ties in again to that relative assessment idea. Accurate assessment of coverage, especially for shorter drive times, really depends heavily on finely detailed data about your roadway system. We're going to spend a good amount of time this morning talking about our roadway system data and how and what we did with that in the analysis. But development of the coverage assessment algorithm focused heavily on getting that high resolution network with a high degree of completeness for the state's true roadway network. And then coverage matches the market when it provides convenient fueling access near fuel cell drivers' homes, near those first market adopters' homes. So this is a fundamental assumption in this analysis and how the analysis is built. There has been plenty of discussion about how to plan for travel routes as opposed to planning for placing stations near fuel cell vehicle drivers' homes. And we'll discuss the differences there later on. But in this analysis, we went ahead and we are adopting this mindset. And finally, the tool must be a tool that can be shared with the public. So we focused on data sources that are non-confidential, data sources that we can share. They may be in an aggregated form, but at least at the form and the level that the data are utilized in CHIT, they are publicly, they're data sets that we can share publicly. And we did all this in ArcGIS. We chose this kind of as our platform for performing this analysis. This morning we spent some time talking about some of these tools in ArcGIS. They're used at various stages. They can be used to kind of explore and validate the data that you are choosing to or considering to implement in the model. You can use them to analyze your results and provide interpretations and meaning to what you have, to the analysis that you performed. We then also, of course, utilize some built-in tools for determining the coverage provided by existing funded and potential stations. And we spent some time this morning talking about overlay actions and how essentially that will tie in directly into our market analysis and then into our coverage gap assessment. We also then, of course, did have to develop some tools that were custom built in ArcGIS using one of ArcGIS's built-in environments for being able to accomplish these kinds of things. So we actually do have this toolbox that we developed, and it is our intent to be able to share this toolbox with the public, and so that you can actually, along with the default data that matches our AB8 2015 report, so that you can actually go in, replicate the same analysis if you use the same data, go through the whole steps, see how the data output is generated, and then for your own purposes, if you want to play around with using this tool and just using different data to see what might come out of it, to be able to have that opportunity. So are there any questions in the room right now at this point, or and online? Okay. So we'll go ahead and move on to our roadway and travel speed data sets. So earlier I showed this map, and we saw an animation of kind of coverage provided by or at least service areas provided by the San Diego station. And a little bit of background, that data was actually, or these service areas are actually calculated using hourly varying traffic data from Caltrans. This is from their performance monitoring system. And we kind of applied that data to a street geometry that's provided by the census called Tiger. Now, one of the benefits of of PEMS is that it's real-world data, and it's all hours of the day, so you can kind of tailor the inputs that you might want to out of that data set and be able to choose your peak traffic time, or if you wanted to look at how coverage changes at different times, you could actually do that by implementing PEMS data. But some of the negatives are that PEMS is limited to highways, and it's not a complete coverage of the highway mileage throughout the state. So if you want to model traffic on roads below a highway classification, that usually requires some kind of assumption of the speed. And usually in literature, assumptions of speed limit are made based on the classification of roads. And when we actually implement this, and we reviewed it, we found that really service areas in many regions are unrealistically large. So, so to provide a little bit more background, that Tiger network that the PEMS data was kind of combined with, it is a finely detailed map. It does not lose resolution in less urban areas. It's true to life, and it can be spatially aligned to other map data sources. But it has no performance attributes. So whereas PEMS had a lot of data, but had very few data points along a lot of the geometry that could be represented, this one has a lot of geometry, but not much information. So again, you'd be stuck with using the road classification system to determine what you might think speed limits are, and that's subject to interpretation. And again, oftentimes using assumptions of posted speed limit is what is kind of the solution that's utilized. So you can continue looking for another data set to solve this issue where you get both high resolution of the geometry and you get good values for attributes for the speed traveled on the roadway. Or you can find another road data set with attributes and project it onto Tiger. So essentially replace the PEMS part of this analysis. And so that's what we have done. We've utilized something called the Integrated Transportation Network. This is an in-house model. It's not publicly posted, but it is my understanding that it potentially could be requested. It is actually the transportation network model utilized for other programs at ARB like MFAC for emissions modeling, spatial emissions allocation. And you can kind of see on the left some of the resolution of this. So the lighter gray on these maps are the Tiger lines, and you can see ITN in the pink line. And Sacramento's kind of in that top left corner to give you an idea of what it looks like resolution on a really fine scale. So the benefits of ITN, it's used internally with other models, so it actually has gone through many rounds of data quality checks. It's kept up by another group in ARB, and they spend a lot of time making sure that this traffic model is correct. It's a stitched together version essentially of the municipal planning organization's traffic model, but ARB goes through significant efforts to make sure that the traffic models output data kind of line up with each other, essentially both in the geometry, but then also in terms of the attributes that they provide. And it provides PM peak data. It actually provides AM peak data, between the peak data, off peak data. So it's a fairly rich data set, including both speed and volume and other metrics. The downside of it, and the reason why we can't use it in its raw form, is that it's not a true-to-life network. It is actually a network that's what's called an effectively equivalent model for planning purposes. So if we want to be able to overlay results from this network with other features that are more true to life, we're going to get a mismatch. And the data density, if you look in this bottom left-hand image, you can see that data density pretty much follows population density. So you get better resolution in your high population, your urban areas, than you do typically in your more rural areas. You can see that you get a lot more of a surface street, in LA and in the Bay Area than you do, in the far north of the state. So what we did was we developed just a simple process, or a process to essentially utilize the desirable aspects of both of these data sets. You have ITN that has a lot of data. It's based on real-world data, and it's based on real-world data at varying classifications of the roadways. But then the geometry of Tiger that is actually true to life. So you need to do a couple of things to actually do this. Since ITN and Tiger don't line up perfectly, you have to fill in the gaps on ITN before you project them onto Tiger, and then you do need to project those attributes. So this is the process where essentially we overlay a grid on ITN, we average within that grid to get a travel speed, a travel velocity within that grid. That then is essentially point data, which we then interpolate in ArcGIS. ArcGIS requires, that does generate what's called a raster, essentially an image of the speed throughout the state. And then what we do is we turn that image into a set of polygons that we can use to essentially cut the Tiger data, the Tiger geometry, wherever there is a change in speed. And then we apply that speed onto the Tiger geometry, and you now have Tiger geometry with attributes. So a visualization of that, we utilize the quarter-mile grid across the entire state to be able to achieve this. So you can see on the bottom left here are ITN lines, and those are colored by speed. So higher speed, I believe in this one is bright purple, where lower speed is a dark blue. And what we do is we overlay our grid on top of that. We average in each of those grid cells, and we get these point data across the state. A couple of notes in case anybody is familiar with ITN or has used it before, or MFAC, or has read up on it. Since it is an equivalent or equivalent model to the real roadway network, there are some linkages in it that are very non-real, and they contain zero flow, but they're there essentially for the solution of the model in its native form, in its original form, to be able to complete more easily. So this is not showing up as well in the room as I'd hoped, but in this figure there are these short, very bright blue lines, and those essentially have zero speed on them, but that's because they're not real lines even in the model. They're simply there to make the solution easier. So we actually remove those lines from our data because that could artificially skew the results. In addition, we need to interpolate. And when you interpolate, you do have to make a number of assumptions. So one of the things we wanted to do was, in accordance with our principles, the roadway data is intended to cover the entire state. So if you use specialized, complex interpolation models that have a number of assumptions or a number of parameters, you need to know a lot of information in order to make those parameters properly fit across the entire state. Simpler, more general rules then were investigated for our interpolation. We essentially do not have enough information to use very complex statistical models to do this interpolation. So we relied on fundamental principles, things that we covered this morning, of geography to be able to do that interpolation. We utilized the inverse distance weighted method to be able to interpolate between the data points on ITN. We also did investigate a statistical model, the simplest one that ArcGIS provides, and we'll show the differences between the two. When we did this, we allowed ArcGIS to automatically tune the parameters. We have a question online.
We have a question online. She typed it in, so I can read it, or Rosie, I can give you the mic. So I will unmute you, and then you can go ahead and ask your question.
Hello?
Hi.
Hello?
We can hear you.
Great. So did you validate this analysis with the traffic study, or maybe ARB already had done that with the ITN data?
Yes, so the ITN data is built from traffic studies and other models. It is itself already validated through ARB, through the other branch of ARB. So we did not personally. I will actually though show some analyses we did as far as how far we deviate after this entire process from the original raw ITN data once we project it onto Tiger and a couple of other steps. But yes, the model itself is built from validated data and models.
Okay, thanks.
Yep. Okay. So one of the advantages of utilizing inverse distance weighted is that it exactly will match your data points at those points. So if you're creating an interpolation model, depending on the assumptions and the formulation of it, you may actually overshoot or undershoot when you go back and look at the actual data points themselves, or your projection at those data points. Kriging, which was that statistical model, assumes that basically the input may be just a sample of real data, and so it's not necessarily exact. It performs a statistical analysis to try to match the distribution of the data, but that doesn't necessarily guarantee that every input point will then be recreated exactly, and your bounds will not be necessarily be recreated exactly. So when you're doing these kinds of analyses in ArcGIS, it provides some way to look at how well your steps have been performed. And down here at the bottom, we have what are called cross-validation plots. Essentially, they're ways to show how well your interpolation matches with the actual data. And so you want essentially a mean error as low as possible, and you want an RMS error as close to 1 as possible. And we can see that when we assume Kriging and we try to use that slightly more nuanced statistical method, it didn't really give us much benefit versus using the really basic inverse distance weighted method. In addition, we found when we looked at the data that the Kriging interpolation over-predicted and under-predicted. So we actually ended up with some negative speeds when we tried to use Kriging interpolation versus inverse distance weighted, and that just does not have a physical meaning. And so what we did at the end of the day decide to use inverse distance weighted. So essentially, this is the result of that. So we went from those points a couple of slides ago to interpolating between all those points. And that's the IDW result on the bottom left. And then once we convert that to polygons, we do actually generalize. This raster is in the form of decimal data, so you have infinite number of different speeds, but we change the resolution of that to 1 mile/hour increments. So your final interpolation is a little bit rougher than the raw raster output. And then so we convert those. We also then get smaller number of unique values to then be able to cut the tiger line. So this is a view of Sacramento region. And what I essentially really want to focus on is you can kind of see the resolution of that, the effect of that quarter-mile interpolation, where we cut the ITN data and averaged it up into these quarter-mile cells, and then how that will affect in the relative size compared to city streets or typical city streets in the actual interpolation. So you can see that on here, the resolution of the interpolation raster is pretty visible. These lines are the tiger lines, and so essentially where there's a difference in the color of the cell, that's where we're going to split the tiger line, and we're going to then have a different value. Jean, did you have a question?
Well, I've been wondering about the interpolation that occurs on the edge of the tiger line. So when you have like a flying spot scanner, you have 2 lines here, you've got a line here, and then you cross over, you interpolate a small amount at the beginning of the later at the end, and then by the time it gets over, it changes the color. So is that what happens here? I mean, are those actually averaged values? Is that why they are straight lines?
So the lines are straight. So the lines are straight. Those are the tiger lines themselves.
A grid. But is it a grid?
No, tiger is not a grid. Tiger is the roadway as it actually, well, as close to as it can be to the actual real streets on the road.
Okay.
Yes, ITN gets averaged on that grid,
okay.
right? And then essentially what we're saying is that we're looking at a quarter-mile grid. We'll get to this in a second, but we found that that resolution was sufficient to be able to accurately recreate the distribution of speed that was in the original ITN data once we applied it onto Tiger.
Okay, then I have a follow-up.
Okay.
So if the speeds are recreated, then how does traffic and vehicles relate? How do traffic and vehicles demand for stations by vehicles, traffic and speed relate when you overlay the?
So the question is, how do the traffic and vehicles relate to the speed overlay? So so the ITN data does also have traffic. When you say traffic, I assume you mean traffic volume, number of vehicles that are traveling on it at a given time. Right. Yeah. So that data is in there. For this analysis, we're basing the cut on the speed, right? So the speed is what determines, when you actually change your value, right, on the Tiger line once you project. We'll talk about volume. We essentially did the same exact type of process using volume as the basis for cutting the Tiger lines and then how to rank them. But the data in ITN is the result of these patterns, right? It's the result of the volume and the street capability that then gives you the speed, right? So ITN is essentially the markers of that. It's the attributes that come out of that. It's not necessarily the analysis that led there, right? Does that answer your question?
I also want you to keep telling us how stations place.
Right.
How does all of this combined data set be used to determine station placement to meet the particular fueling needs? Yeah,
I promise we will get there. This is one of the more in-depth parts of the analysis because this is fundamental and key to our coverage analysis. That we have this high-resolution data set that really looks at speeds on the surface level streets, the city level streets, not just the highways. Because when you're looking at shorter drive times, that becomes more and more important. Okay. All right. So we are getting there. I promise. It's a few more slides, but we'll get there. So just to show you. Oh, sorry. We have one other question.
Sorry. I closed it the wrong way. Can you iterate why Caltrans performance data could not be used? Question from James Provenzo. I'll put you on. I will unmute you, James.
So the reason we did not use the Caltrans PEMS data is that it is limited only to the highway system. And when you are looking at trying to model 3-minute, 6-minute drive times, you need data on streets below that classification. We did talk to Caltrans about data that they might have, databases or models that they might have for lower or for all the streets essentially, and their response to us was that it is not something that they have at this point in time. It is something they're working on, but they do not have that available.
Okay, that's clear. Okay, so only primary streets primary highways and streets were used. Not the secondary streets are not in the Caltrans data.
Right, not in that data set that we investigated. Okay. Caltrans.
Good enough. Thank you very much. Thank you.
Yeah, like Nicholas.
So how does this differ from just use standard Tiger? They've got speed limits, and order of magnitude, the speed limits are representative, and then especially looking at over different times of day, how do you know what to do with it?
Right.
They can refuel over once over a 4-day period, and so these things shrink and grow. Like what relationship do you think that has to refueling?
So the Tiger data that we saw, utilizing speed limits that came from PEMS and utilizing data that's available in Tiger, we reviewed the drive times that we were seeing in the service areas, and they were unrealistically large. My take on that is that those speed limits, speed limit is one thing. Traveling speed is totally different, right? And essentially, and you're right, your areas change as you go throughout the day and at different times, and people refuel at different times. But we are trying to look at the worst case scenario. You know, the person who is having trouble at 5 o'clock in the afternoon getting to a station that we tell them is 6 minutes away and it's taking them half an hour, that's really the issue that we need to address.
The effect might be you would densify stations. If you take the worst case scenario, you would densify stations.
Yeah.
So people could, you know, they wouldn't choose when to refuel. They'll do the worst case.
Right.
Okay.
Yes, we are. There's an implicit assumption there of trying to accommodate people wanting to keep their likely
it's the only
refueling cost.
You'll be able to differentiate congested areas from non-congested areas. You could also just take Tiger data and speed limits and, you know, cut it down by 20%. You might end up with similar things. But, you know, congested areas would be different than non-congested.
Right. Yeah, we could do that. We could make assumptions like that. I guess in our estimation, it was better to utilize another data set that was validated, had all that behind it, rather than just we're going to cut it by 20% and we think that's okay, right? So since we had this ITN data set available in-house, we went ahead with that.
I have another question.
Yeah.
Elise, I'm going to unmute you. Her question is, how recent is ITN data? Is it an average over a number of days?
So the ITN data is the average. We use the average PM peak, I believe, for the weekday. ITN does provide you different times of day to choose. And in terms of how recent it is, we actually, pretty close to finalizing our AB8 report, became aware that the 2015 version of ITN was available. So right before the 15 report, we redid all our analysis with the 2015 version of ITN, which includes data up to December of 2014 from the municipal planning organizations. I don't know if that means every municipal planning organization's data was from 2014. That just means that the most recent data was 2014.
Okay, thank you.
Yeah.
So behind CHIT, how often should station developers and OEMs and everyone else be ready for new data sets, like new Tiger data to come in? Oh, and is it relevant, or is it such a finite difference that it wouldn't be?
So I think I have it in the backup slides, and if we get there at some point, if we have time at the end of the full discussion, I'll show it. But there was a little bit of a difference between 2012 ITN and 2015 ITN. So those were the two different data sets we looked at. Probably about 10% difference in the size of service areas based on those different data sets. In terms of updating the data, for our analyses for AB8 and reports, we're likely to update possibly annually. We do look at demographic data that does get updated annually, so we might choose to do that. But I don't anticipate that 1 year to the next, the data is going to change drastically. As discussed this morning, our demographic data, we use 5-year averages. So, you know, you're already averaging over a long period of time at that point. Dwight?
No.
Oh. All right. So here is kind of the result of that interpolation, that image file that I had mentioned, and then this is the result on the right once we, you know, turn that into geometries that can actually cut the Tiger data and we project it down onto the Tiger data. And the effect of that, kind of like to show, this is an area near the Santa Barbara station. You can see this long chain. So right here, we're coloring not by travel speed, but by travel time. So this one long chain has the same travel speed. It takes, you know, a certain one color of travel time, essentially, right? And that's in the PEM Tiger data, if you just assume a speed limit for that road based on its classification. But utilizing the ITN data, you can see that you have much finer resolution. Different parts of the road take a different amount of time to traverse, and so you get a better sense. You know, you get finer detail more resolution essentially on the roads that you actually need to be able to interpret for these service areas that are going to be important in the coverage factor analysis. So I promised we'll talk a little bit about the validity of this method. So we looked at the distribution of speeds in the original ITN master data set. We can count speeds in two ways. You can either count it in terms of how many links are at a certain speed, or you can count in terms of the mileage at a given speed. So if you plot the distribution of it, it looks like this as you see on the screen. And then if we do the same thing and we just after our gridding step, we go ahead and plot the distribution, we know that it's not going to be exactly the same because we are averaging in that step. We don't expect 100% the same, but if they were exactly the same, they would lie along this line, this one-to-one line. So what we're plotting is the average gridded data versus the original master ITN data. And we can see we do have some deviation, especially at the high end of speeds, but overall the fit seems to be pretty acceptable here, R squared of 9.97 almost. And then once we move from just the gridded point all the way through the interpolation, which can include its own math, its own averaging, then through the polygon generation and cutting ITN or cutting Tiger by those lines and generating Tiger ITN, now we can compare both mileage and linkage counts on their distributions, and we can see that we pretty much kept the same fidelity of the data. We didn't lose too much of the initial distribution of the speed. And importantly, with this whole IDW, we maintained this whole interpolation method. We maintained the range of data that we had in the original ITN. So the minimum value and the maximum value were the same once we did all this projection and all this interpolation. Of course, there were many steps along the process, things that could have been improved, and we did actually investigate a number of these options. So, but we found they didn't have a significant effect. So the first is that when we average in a cell, we don't actually account for the different lengths of all the lines that might be in that cell. So you might want to weight the speed that you count in that cell based on how long the road is that's at a certain speed. We did that, we tried that, went through the whole process again, looked at the whole distribution, didn't have a significant impact. We decreased the resolution to 1/8 of a grid cell. It took forever to run, but we also, again, found it didn't actually improve our estimation. And then we also did a method where we didn't have to average in that first step, where we actually just interpolated directly from sample points taken at 1/8 mile increments along each of the lines in ITN. And again, we did not see an improvement in the match between our final results and our original ITN data. So, considering all the options that we did look at, there may be other options to improve it, and we'd definitely be open to hearing any thoughts on that. But considering all the options that we did look at, we settled on using IDW, non-weighted averaging, in cells of quarter-mile resolution. Again, IDW ensures that the predicted value at the locations from the original input data are actually recreated, and we had no negatives and no overly high values like we did with other interpolation methods. And increasing the resolution and weighting our average did not help our value. So to how this all ties in now to an evaluation in CHIT and where we need to put new stations, this will become a key input for determining existing coverage from existing stations. So up here, we're going to look at a few slides of what the projections are for different drive time, different service areas from all the existing and planned 51 stations under three different types of data. So this is a PEMS Tiger. The one that I told you earlier did not give us too large of areas. This is at ITN. So we actually did also investigate not doing any interpolation, just taking ITN as it is, just assuming even though it's not a real-world network, it is still going to be usable. At least we didn't have to do any averaging. Maybe it would give us a still workable set. And then all the way on the right is our ITN Tiger, which is the result of the process that I just explained. And so these are all the stations in the Bay Area. You can see Thames Tiger, they're all very large. You see ITN brings them a little bit smaller. ITN Tiger, they're the smallest station, or smallest service areas. You can see when we start looking at the LA and OC stations that one of the major effects here is you start, because you have smaller service areas, I guess your assessment of how much these are providing a clustered coverage would be much different versus if you had only the Thames Tiger data. You might see that these stations are starting to provide very high clustering and very high coverage, but with this data set, that's not the case. This is Sacramento. Thames Tiger really did not make much sense that you could get this far within 15 minutes, all the way out to Folsom Lake. And then this is ITN, and then ITN Tiger. San Diego. I'll get one more slide. And then finally, this is the real reason why we didn't use just ITN. We didn't use ITN because, as I mentioned earlier, the more rural you get, the less resolution it gets. So our station in Truckee, we would not be actually be able to analyze the station at all. And this is intended to be a tool that can be used year in and year out. We're sure it's going to have improvements throughout the years, but we don't want to change the fundamentals of it every year. So as we go through time, we're going to be getting stations in less urban areas as we progress, and we want to be able to still project the coverage provided by those stations or proposed stations in those areas. So we couldn't simply just use ITN as it was in its native form. That's why we had to go through this entire process to get this ITN Tiger. And we have a question in the room from Jim McKinney.
Yeah, and if you could go back to the LA slide that you had up in this series.
Can you grab the mic?
Okay. Yeah, thank you, Andrew. Could you elaborate on that point you were making about clustering and why ITN Tiger was superior in analyzing that effect?
Well, we're starting from the assumption, or not the assumption, but the analysis that the Thames Tiger data gives you service areas that are too large. And so when you get those service areas that are too large, in LAOC, it's starting to show you that you might be getting clustering coverage, overlapping coverage, right? And that's essentially when you start thinking of coverage in terms of degrees, you might start saying, okay, well, those areas are starting to get really well, they're pretty much set then, right? You might be able to say that at some point soon. But when you use ITN Tiger, you start seeing that, that overlapping nature, that's not quite as big of an extent as Thames Tiger would lead you to believe. And so with this higher resolution data set, you're getting a better sense of how these multiple service areas are starting to overlap. And we believe it's a better sense of that.
Okay, thank you. And then the follow-up. So in terms of clustering, does that start to factor in the capacity? So in terms of volume of fuel needed to meet a given market demand, so given that LA is probably one of the densest and kind of highest demand areas in the state for this, is that where this analysis is leading?
Yeah, that's the very end of the work today.
Like Gene and wait till the end.
Yeah, sorry. We did put capacity at the end, but
that's great.
Yeah, it's leading there. Do you have any questions online?
I just checked and I didn't see any.
Okay.
Let me check one more time.
We have a question from Gene.
Okay, so the LA area, so I got why it's important to have both systems for rural, but it seems like it's equally important to have both systems for the urban.
Yes,
okay.
It is. Yes. Okay. And as an example, I guess it's hard to see in this slide, but we hear a lot about the Torrance cluster as it was defined in the partnership document, partnership roadmap. And with this Thames Tiger, it looks like you've got plenty of really short drive time covered by the Torrance station and the Harbor City station. But we do hear a lot that there's a lot of trouble that those two stations may not actually provide sufficient coverage even alone. And you can see that you're getting less of that overlapping coverage in the ITN Tiger, right? So that's I didn't zoom in on that for these examples, but that is one of the things we kind of saw as we went through this analysis. Okay. So, and to put some numbers on this, when you compare the size of drive times throughout the state from all 51 stations between ITN Tiger and PEMS Tiger, you see they're significantly smaller with the ITN Tiger. So we demonstrate a significant difference in the service area, and therefore, as we're about to get to it, the coverage between these data sets that relied only on measured data from the highways versus relying on measured data from the highways and the surface streets, essentially. Yeah.
So actually, back to my previous question, now it's like about 40%. And so, could you just make an estimation of 40%, or sorry? I was looking at these numbers; they all seem fairly consistent. There's 6 minutes, 40 minutes, so it's like 40, average of 40%, or maybe a little bit higher. Does this differ from those different regions? So ones with congestion and ones without, and why are you giving it one number if it actually is really different?
Right. So this was just to give a general sense. I did not, not showing. I did not get the range of different areas covered by in different service areas in different regions.
It'd be really interesting.
Yeah, I can get that as a follow-up. We have a question online.
There's a question online, James Provenzano. I'm going to unmute you.
Thank you. I really like the way this is breaking out, because the ITN Tiger is starting to show islands of serviceability, and that's really how a consumer will look at these stations where they're where it's actually feasible to go to. So I think the resolution of the ITN Tiger makes sense, and as a customer of these stations, it really highlights how I've looked at the areas, especially in the LA region, and it's very accurate on an anecdotal level. I have the question I have is possibly for Gene and or Jim. How is this tool going to be used in conjunction with the street model in future ponds?
So actually, I can take a stab at that too. So this model or this tool has been utilized by ARB to determine what we identify as the priorities for new station development, and CEC has taken those recommendations and they've integrated them into their solicitation concepts already and developing solicitation. So in terms of implementation, as you saw in the solicitation concept, we'll get to it again later in the presentation, but all this comes together in terms of that coverage assessment that then combines with a market assessment and gives you a coverage gap. And that's essentially, I'm using the word value, not a score. The value, and that value will be utilized in some way by CEC when they score applications. There's also plenty of room in the applications for applicants to also provide additional information if they believe there's important information about their particular site that was not captured by this model.
Okay, thank you.
Yep. And one more question online.
Just to reiterate to the people in the room, I'm getting a lot of comments from folks online. They cannot hear your questions. Please wait until you get a mic.
Thank you. So there's not a question online then. Okay. All right. So some of the details of this analysis. One is turn delays, mentioned earlier this morning. So we did not use turn delays in these results so far. Our GIS does give you the option to essentially say how long do you have to wait for a left turn, a U-turn, a right turn. As far as we were able to find in the literature, there's no apparent consensus on typical values, and it's probably because this varies so much, depends so much on your location, where you are. So to be able to do, you can actually, if you want, implement turn delays specific to every intersection. But we're doing an analysis for the entire state. It's just not feasible. So what we did was at least to look at this to see what the effect was. We assumed some values that were based on a set of values we found in literature. So 2-second delay for I believe that's a drive straight through, a 6-second delay for a left turn, etc. And we then reran the service area analysis, and we saw some differences, but not a lot. Just to go through these kind of quick. And overall, to put numbers on it, it makes a bigger difference, obviously, on shorter drive times, right? And so we do acknowledge there's a difference. We do acknowledge it can have an effect. But this was a simple case study based on a really rough estimate of what those turn delays would be in a global sense if you just put the same number at every single intersection. And that's not really realistic model of the world, and we don't have the resources to find turn delays for every single intersection in the state, and we weren't really able to find a proven generalized rule. So we did stick with the solution that did not have turn delays implemented in it. All right, so that's the end of the discussion on the actual traffic data set. And that all leads into the coverage calculation, which is part of our analysis. So in coverage algorithm, so that whole development leads right into this. Those service areas that we calculate based on the drive times from ITN Tiger, those are the basis for the representation and estimation of coverage provided by existing stations. You can also utilize that same data set to estimate coverage that might be provided by potential stations in the future. So we wanted to provide an estimate that was not just yes, no, a binary decision. We wanted to allow estimation of degrees of coverage. We want to be able to say that somebody who has a station 10 minutes away from them has less coverage than somebody who has a station 2 minutes away from them. Somebody who has 2 stations within 12 minutes has less coverage than somebody who has a station within 12 minutes and a station within 3, right? So we actually do estimate the combined coverage provided by multiple stations that may be reachable within various drive times from a given point, all these different points in the state. To get into the math of the algorithm, we use the same quarter-mile resolution grid. And let's say you have these 3 stations arranged around the state, and we're looking at these 2 grid cells, and we want to assess what is the coverage in those 2 grid cells. What we did was we essentially assigned a scoring algorithm for different drive times. And the shorter your drive time, the higher the score. So 6-minute drive time overlaps a cell from a station. 1-minute drive time overlaps a cell from a station. That station contributes a score of 6 to that cell. 3 minutes would be 5, and so on and so forth, all the way down to the 1-minute drive time. You add up all those scores, and then you take the inverse of them. And that gives you your estimate for coverage provided by those stations. So as you can see in this example, the top right cell, it only has a 1-minute drive time coverage from that bottom right station, so it gets a score of 1/6, whereas the bottom left cell has 2 stations that are covering it at different times, so it gets a score of 1/11. That cell right there, that bottom left cell, is less desirable for a new station because it has more coverage. That's the reason why we did the inverting. We wanted to turn this into an estimation of desirability. So in terms of the algorithm in CHIT, that does require essentially iteration through all the drive times for all 51 stations. So the way that our tool actually achieves this is it initializes a temporary data set, and then it sorts and groups all the service areas from one station. So it picks the Woodside station, say, and it identifies, it looks at all those service areas, it overlays that analysis grid, and it picks the shortest service area in every cell that has an overlay with that station service area, okay? And then it creates a record of which station overlapped it, what cell that is, and then which drive time it was, the shortest drive time that overlapped that cell, and you go through all 51 stations. You then take that list of records, and you analyze it in each cell, and you assign those scores based on the drive time you recorded here and the algorithm on the previous slide, and then you overlay that again with the analysis grid and sum them up and invert them, and you get your value. So down here, this is essentially that transformation step. These are the drive times from all the stations around the Bay Area, from 1 to 15 minutes, and you can see them colored in on this figure, where you can actually see all of them or most of them individually. And then after the algorithm, you kind of get this. You get this color shading is indicating that this area right here, this high red area, would be less desirable because it has a high coverage already. This has the most coverage. You can kind of see that all these drive times are overlapping down here in this region. So again, more stations and closer stations mean a higher coverage. Later on, that will then mean a lower coverage gap score. And again, this morning I showed some of the actual ArcGIS tools that we developed for this. Again, we are planning to at some point be able to distribute this toolbox. So for people who may end up being interested in playing around with it, looking at what the actual workings of it are, this is essentially our determine drive overlaps and generate coverage factor tool. So the determine drive overlaps is the one that iterates through all the stations and does that kind of builds that record, that temporary record, and then the generate coverage factor takes that record and actually performs the algorithm that scores every cell. Do we have any questions online about that? Any questions in the room about that? Yeah.
Desirability maps. Those desirability maps, are those analogous to the desirability to purchase a car or to use the station?
Those are. Did you reword that?
There's usage. There's purchase and usage. There's two different things. And, people may view them differently. Consumers may view them differently. So I would say usage is a much. I don't know if I can refer to usage.
So this is. Are you getting to the market in terms of where?
Yeah, I mean, it looks like these could be actually fairly useful for market estimations to convince people to buy the car. But as far as the usage, you might have to go at it a little different way, based on some research that I've seen. Okay. Yeah. Well,
I guess the most direct really is that this is just an estimation of the coverage, right? So we're going to eventually get this with the market. So if coverage was your only thing that you were looking at, then yes, I was just saying this is formulated in terms of higher is less desirable because it already has more coverage, right? More neighborhoods that it's servicing essentially, or the neighborhood is serviced by more stations. Yeah. And that is within that original principle that we're looking to place stations near the neighborhoods where the first adopters are living. That's part of our built-in principles on this. So in addition to existing coverage, you could also assess the coverage that could be provided by placing a new station in a new location. So again, we looked for a method that could be applied statewide. This is our potential coverage factor. This is treated as an input to the model, so we calculated this. This is an input data set. It doesn't need to be recalculated every time you run the CHIT model. And it's formulated as a method to answer the question as a potential site, and you need a pretty high resolution set of potential sites to be able to do this, and we modeled that as the centers of block groups. So we discussed geometries this morning based on census geometries. How many households will have access to me within a given time frame? So we went with just the 1 6-minute time frame for this analysis. Partly motivated by need for computing time and all of that. We utilize those block group centers essentially as a relatively high resolution set of surrogates for where you could put a new station. You could theoretically go to an infinite resolution for where you might put a new station and come up with a value. But we use those block groups as that set. And then we utilize an interpolation method similar to what you saw this morning from IT and Tiger to be able to fill in the gap between those data points. So for example, this is kind of zoomed in around, I think it was around Oakland or Emeryville. So if there's a block group, this is our seed block group, and we calculate the 6-minute drive time for that block group by this, indicated by this green outline. Then we overlay that with the positions of all the block population data from the census as well, and we add all those households up. And we then assign that back down to the source block group centroid. So basically we're saying if you put a station here, how many households can be serviced within 6 minutes by that station? Okay? And then you simply repeat that analysis through every single block group throughout the state. It does look a little funky in terms of once you actually do the interpolation, but essentially then once you have that data throughout the state, you interpolate and you get your map. It is then, of course, dependent on population densities because we're using block groups as our centers of block groups as our kind of our resolution for this map, for this interpolation map. And so those are our coverage factors that we analyze. So that's 1/2 of our analysis that tells us how, where are the priority areas. And are there any questions online?
No, no question.
So we've gotten a lot of feedback about traffic patterns, and we definitely do realize, and we've heard a lot, that traffic patterns might be a different and maybe even might be a better method for looking at how to site stations. That you might want to site stations to be near the normal traffic routes that people, or common traffic routes that people traverse. We did not. Well, actually, here we go. So first of all, in our tool, we, again, just to reiterate, we took the principle that convenience is provided by stations within short drive times of vehicle owner homes. Okay, and that again also does tie into what we've heard, or what has been discussed in terms of being able to boost fuel cell vehicle adoption rates. That alternative principle is to look at short deviations from commonly traveled routes. Explicit and direct consideration of this, being able to actually calculate this, requires what's called origin destination data sets. We tried to look for this. We tried to find a data set that could cover the entire state sufficiently to the same kind of degree as we got for the ITN Tiger, but we weren't really able to find a data set that did that yet. As an alternative, and maybe as a surrogate, we thought, okay, well maybe what we can do is we do have volume data. We have volume at the peaks and off the peaks from the ITN data set. So if we apply the same kind of analysis that we did for speed, but use volume, maybe high commuter traffic lanes and high commuter traffic areas might be indicated by areas where your peak traffic, your peak volume makes up a much more significant portion of your total daily volume. And so we tried to look at that, and we did see that there's variation across the state, and in some areas there is some variation even on a smaller scale. But when we kept looking all across the state and looking at the quality of this estimate, it didn't really work out. You see really large areas where essentially you'd get that no street in this area just using volume data would be indicated as a high commuter area. So at the end of the day, we recognize that this idea of origin destination and looking at common traffic routes might be a better way to go, but we could not identify a data set that worked to explicitly implement that, and our kind of best guess estimate with the data that we did have wasn't really working out for us yet either. So we have heard a lot of information about this, or a lot of interest in this, and if people have information that they want to share or willing to share, or suggestions, that's definitely something that we would be interested in hearing, and in order to be able to improve, the estimations of this model, of this tool. We did actually also investigate other data sets that might be able to provide volume data, origin destination data, but essentially, again, they just weren't high resolution enough. This is one example of those data sets, and again, you can kind of see that it's similar to the PEM data. It really just follows the the major highways. So our principle of having data sets that can actually provide consistent analysis basis at varying levels throughout the entire state just couldn't be met for this type of analysis. Yeah.
Is block group fine enough?
I'm sorry?
Block group, I know you use blocks, but is block group, is that fine-grained enough for origin destination to be useful?
It might be. I haven't.
The block group's slightly bigger than.
Yeah.
Yeah, tract is a little bit bigger, but block group is, you know, typically, I don't know, maybe 600 households or.
Right.
Something like that.
But I guess the data sets that we saw, that maybe in certain areas you would have like resolution in terms of, you know, small area, you'd have a very high resolution. But then in other areas of the state you wouldn't have much information.
Yeah, it would be when you get very, very small
right.
populations,
right.
then it doesn't really contribute as much to the demand. So
yeah.
Trade-off, and it might be okay. But
right.
So if you want to download our tool, we have a data set for employment data. So it's taking tax records, loads data, and has a origin destination matrix for commuters.
Okay. Is that the
California?
Is that the no? But your tool is
so it's the it's the EV.
Right. Yeah. Okay.
But it could be useful for those to do.
Yeah.
At a fairly fine-grained level, so it has every block group to every other block group.
Okay. Thank you. Yeah. Do you have questions online?
No questions.
Do you have any other questions in the room at all? All right. So we discussed all the coverage calculations that we performed in our CHIT analysis. So now we're going to discuss the first adopter market assessment. And so similar to some other works, we are utilizing a number of demographic-based indicators for determining areas where fuel cell market, early market adopters are likely to be located. There are three main categories of indicators here. There are financial indicators, green vehicle adoption indicator, and an education attainment indicator. It's important to keep in mind that we're overlaying these indicators, but we're not necessarily saying that in that process that we're finding all the households where everybody makes a certain amount of money and owns at least one green vehicle and has a certain degree. What we're doing is we're looking at the spatial patterns of these individual indicators, and where they're, you know, matching up in terms of peaks. That's where you might have a higher market. So we incorporated factors that appear in literature and from discussions with stakeholders. So this is based on ARB's best up-to-date estimation and understanding of what is important in this kind of analysis. The geographical resolution is based on the data source. So this is where we're combining some different data sources. So income comes from census data on the tract level. And then vehicle data comes from the DMV, which we discussed this morning, is on the zip code level. And then education is similarly from the census on the tract level. So we'll step through each of these. We'll spend a little bit of time on the financial indicators and how those relate to each other. So the first is the income factor. We do anticipate the first market vehicles will have a retail cost premium, and therefore the first adopters are likely to be in high-earning households. For most of our data projections in our analysis, we looked at the 5-year ACS 2013 estimates. But to give us kind of a starting point, we looked at the 2014 ACS data and found that on average, the top 20% of earners made $230,000. It so happens to be that the top 5% in that 5-year data, the cutoff for that is $230,000. And for purposes of trying to model income and trying to assess your modeling of the income distribution, that was an easier metric to utilize. So you'll see that when we assess how well we're actually interpolating income, we're looking at 5%, top 5% making 230,000. The ACS data provides a challenge because at the statewide level, we know 230,000 is the average for the top 20%. But when you look at the tract level and you look at the income distribution data available, it caps at $200,000. So you have to do some modeling of the income at the tract level in order to be able to actually figure out what percentage of that tract population are in this market that you're looking at. We considered a number of ways to do this. One was just a more qualitative method, looking at where in the distribution that cutoff sat and trying to just give a score to that. We've modeled tract level income on a log normal basis because that has been used for many years to look at income distribution in economic studies. And then we looked at the exponential distribution as well. And we're going to compare each of those. So assuming that you cannot or do not want to go through the process of recreating the distribution of income on the tract level, one thing you can do is essentially say, okay, I know the cutoff I'm looking for is 230,000. Is that in the top 20%? Is that in the top 5%? Top 40%? Top 60%? And just locate that value for every single tract, and then assign some kind of score to that. So the benefit here is you're not interpolating, you're not really transforming the data too much. The negative is that if you pursue this kind of method, you then have to come up with some scoring criterion for saying, okay, in the top 5% receive a score of X, and the top 20% receive a score of Y. So here is that essentially plotted on the right-hand side, that income. So this is just one method we looked at. The other is that with the summary statistics available from ACS, you can actually, with only a few assumptions, try to recreate what the income distribution is at the tract level, essentially using the median and the margin of error. So we utilize a statistical inference method based on log normal, and the median and the margin of error, and essentially then estimate what percentage of the households in each tract are above that $230,000. And then when you do that in every single tract, you add them all back up, compare it to how many households there are in the state, you get pretty close. If you're looking for 5%, you got 5.7%. It was pretty good, but there's still some unknowns here. The ACS documentation is a little unclear on the formulation of their reported medians and how they arrive at the margin of error. And then also, 5.7% is still about 20% higher than you want it to actually get to. So we decided to look into this a little bit further. These are the two side by side. You can see that there are some spatial differences between these two methods. And so working with other staff at ARB, actually some economists, some statistical economists, we identified recent works that indicate that income distribution is actually kind of two different functions depending on where on the income scale you're looking at. At the lower end, it might be log normal, but at the higher end, it might be more exponential. So what we did was working with that, with research division staff, he helped us derive a method to essentially look at what's called the survival function. If you're familiar with statistics and you know the cumulative distribution is essentially the inverse of that. And so what we did is then said, okay, we're essentially having to extrapolate beyond the data. The data, as I mentioned earlier, only shows you how many people are above 200,000. So you have to use this data as best you can to kind of extrapolate, well, what's above 230. And so what we do is we utilize the last 3 data points here, fit to an exponential curve, and then extrapolate what the $230,000 proportion is. And when we do that on every single tract and we add it up, we get a much better match. We get 5.1% of households when we were looking for 5%. In addition, the range of the quantiles, where the range of how many households on each tract are at this cutoff or above, was closer to the original data. The range was between 0 and 58% when you use an exponential model. It was only 0 to 30% when you use a log normal, and from the data that was not transformed at all, it should be 0 to 60. So this was a much better match. Again, I'm not going to go through this top bullet and all this reading. Maybe when you look at the slides later, you can read through that. But visually, as an example, this is an example of a tract in Alameda County, and these are all the cutoffs for the different quantiles and their means, right? And if we look at this county, we're looking for 230,000, and the data indicates that it's between the top 30 and the top 40% of that in that tract. If we use our log normal model, our log normal statistical model, we would get that all the way in the top 13%. But if we utilize our exponential model, we get that it's in the top 32%, which is in the range of the original data. And this was pretty much repeatable throughout many tracts in the state. So we did eventually choose to go with this exponential distribution. So here are comparisons side by side. In these maps, all the scales are set to the same as the quantile data. So basically, essentially at the higher end, at these higher ends of data, we find a much better match when we utilize the exponential distribution versus the log normal distribution for modeling income on the tract level. And the key point is that is really where what we're looking at. We're looking at the top 20% in our model. So it was important to get that right. Do we have any questions online? Okay. Or in the room? No, it's a little bit in the weeds, but just so you, okay. A little bit in the weeds, but to clarify why we went with some of these assumptions. Then looking at vehicle attributes, we utilize multiple vehicle-based attributes that we investigate as additional factors. They're all based on DMV data at the zip code resolution. And there were 3 of them that we looked at. There are indications, historically even you can kind of see this, that luxury brands typically get the technology first and then it trickles down. So luxury brand buyers may be more likely to be first adopters of vehicle technologies. And so what we did is we looked at counts of registered luxury brand vehicles in the last 5 model years. We looked at the MSRP range. So in the DMV data that we have, it includes a range of MSRP values for all the models. They're reported, I believe, by the OEM. And so we looked at what was reported for the pre-commercial fuel cell vehicles. We looked at what, the announcements that are made, and we compared that and decided on a range, a low value range and a high value range, in which to count all other vehicle registrations within the last 5 years that fall within that same range. So essentially, we're trying to find vehicles that likely had the same or similar MSRP to what will be coming out for the fuel cell vehicles at commercial launch. And then we looked at first adopters of green vehicles. So first adopters of previous technologies may be more likely to become first adopters of the fuel cell vehicle. One thing that we implemented is that we did not include BEVs. We included hybrids and plug-in hybrids based on the assumption that these are alternative fuel vehicle technologies that do not require a change in fueling patterns. And so since what we're doing is one of our core principles is that we're looking to provide convenience to people, to the first adopters, in terms of not having to change their fueling patterns. What we did is we looked at the first 8 years of hybrid vehicle adoption, because based on other research that indicates how long the first adopter market might last, and then the first 5 years, essentially, of, I believe, of plug-in hybrid vehicle adoption, since there haven't been 8 years of that yet. Yeah.
Right, one thing you might look at is PHVs, and a lot of people, what drives their decisions is carpool sticker. So
right.
If you have a long range, like Tesla's like a long range white sticker, which is probably not go anyways. But the green sticker sales would probably give you a little inkling of why people might spend the extra money for technology.
Yeah, yeah. There may be many motivations behind the different green vehicle purchases, but unfortunately, when you get the DMV data, you don't get why the person bought the vehicle, right? So we could utilize purchase decision data to try and scale back our numbers, but
Yeah, well, you can do some. You can look at where all the HOV lanes exist. There's a just look where all the HOV lanes exist, and then look at the green sticker registration. I think that you might be able to get some data on or some estimations based on how many people got some green stickers, and just say, okay, well, we're going to take 70% of them. It's something
right.
like that.
Yeah, yeah, that's okay. Yeah, that's something we can look at.
In the research that we've done, it was actually a great motivator.
Yeah.
If people didn't get the green sticker, they wouldn't have bought the car.
Yeah.
So this is like another way to get in the carpool lane when the green stickers run out.
Right. All right. So, going through each of these, you look at luxury vehicle registrations. There are essentially over 1 million total registrations with sufficient data quality. Oh, we have a question. Sorry.
James Provenzano, you're unmuted right now. Are you there, James?
Oh, hi, thank you. Yeah, it's James Provenzano. What were the assumptions on based upon the early adopters and current owners of luxury vehicles, and is that based on OEM stats, or is that an assumption, or?
Some of it's information that we've seen in the literature. Some of it is assumption. Some of it is discussions we've had with stakeholders. It's essentially ARB's most current understanding of the factors that might be at play in the early adopter market.
Yeah, because it's interesting. I would think green vehicles might be a better indicator of purchasers of green vehicles, the actual clean technology, where I think current luxury brand buyers will most likely buy a luxury brand clean vehicle. They might not necessarily buy a lower end clean vehicle. So, and vice versa. There are a lot of people that will buy new technologies but are not necessarily into luxury brands. So that's just an interesting one. I think the green vehicles purchases of green vehicles, in my opinion, just in the people that I know this is low data points, but it is a better indicator of people that actually own luxury vehicles.
Okay. Thank you. Okay, so looking at that actual data, this is essentially the distribution of it. We looked at these brands in terms of what was a luxury vehicle. We weren't necessarily looking for the super exotics, but there are a number of vehicle brands and makes that should cover a good portion of that estimation. And then when we look at the MSRP, essentially what we did is we looked at various metrics from the MSRP that was reported for the pre-commercial fuel cell vehicles, and again the announcements that have been made so far. And the high-low range we essentially ended up settling on, based on all the information we were looking at, was a low of at least 50,000 and a high of at most 75. And then essentially we looked through the DMV data for all the vehicles that fit within that range, and we plotted, and here you can see those plotted out again, where bright purple is high, low, or bright blue is low. And if we kind of just scroll back and forth, we can see there definitely seems to be a lot of overlap between these two. So qualitatively, when we look at those two and income, there's a lot of match between the spatial variation in those three factors. Conceptually, they all have some element of finances or income. One of them is directly income. So we did look at the spatial covariation, essentially how much do these factors actually change the same across the state with each other. We did find that actually, a little bit surprisingly, the spatial patterns of MSRP were more related to luxury vehicle registrations than income in terms of the registration. And you could improve the model a little bit when essentially MSRP, luxury and income, or MSRP as a function of luxury and income had a match of about 58%. So what we essentially came down to was that both luxury vehicles and income are statistically significant factors in the purchase price. And essentially, all three of these are related, and they're more related in some areas than others. So here what we're looking at is a bright red means that, for example, in this leftmost figure, MSRP is highly correlated with income in these bright red areas. Over here, MSRP is highly correlated with luxury, and then with the combination of the two. Oh, I thought I had another slide here. But essentially, what we found was that there are areas where they're highly correlated, but at most you could explain 60% of the variation from in any one of these three with using the other two as a surrogate instead. And so essentially what we decided was that that was a pretty close match, but it wasn't high enough to say that you could throw out one of these three factors. So they definitely do have a common basis, but they may not be close enough to actually get rid of any of them. And then, as I mentioned, we looked at the first, the 8-year period for the first adopter market, looked at counts of hybrid vehicles from model year 2000 to 2007, plug-in hybrids from 2010 to 2014, greater than 300,000 total registrations with sufficient data quality here, so you can see that distribution on the slide. And then we looked at education. There are some indications that areas with households having increased education levels may be more likely to be early adopters, particularly of green advanced technologies. So we utilize census data counts of the number of postgraduate degrees in the population 25 and older as our indicator for that. And that is essentially all the data, all the information, all the data sources, how we represented it, how we accounted for it in our assessment and everything that goes into this CHIT tool. And the next step then is to analyze that data to be able to identify what the priority areas are for new stations. So this is the most direct step in terms of what this means for the next funding opportunity. So the way that we perform this evaluation, again, we compare the evaluation of the market and the coverage to determine the gap. We can look at market potential separate from just the areas with the highest need, this allows us to do this annually and adjust our planning as deployment progresses. So we move from those drive time calculations, that Tiger ITN we talked about earlier, translate that into a coverage analysis, put together our market assessment based on the factors we just discussed, and we come up with a gap. So actually, if you were at the CEC's PON workshop in August, you've seen this slide before, but essentially we overlay all these different factors that we consider to be important to identifying the early adopter market. We take a weighted summation of them, and that gives us our market. That gives us our full market assessment across the state. And so in terms of how you achieve this in ArcGIS and in CHIT in particular, this would be the Generate Heat Map tool that we created. This is actually, it's long, but it's actually just a lot of very simple calculations. So before you go into this tool, all of the data needs to be normalized by the area of all the associated features. You overlay your analysis grid with each one of the indicators or each one of the factors, and you aggregate as appropriate. So you might need to average or you might need to sum depending on which factor you're looking at. You normalize each of those factors internally. So this gives you your relative assessment of how each of those factors might impact your full coverage gap assessment. And then you compute that coverage gap according to the desired weight for each of the factors. And so normalizing each of those factors by their internal maximum, everything is then just a 0 to 1. So if you had a perfect match between, you had the best market indicator, best market by all indicators, and you had no coverage at all, you would have a score, a final heat map score of 1. If you had all the best coverage already and you were low market, essentially you could have a heat map score close to 0. And so in that assessment, we have not done yet a sensitivity analysis on this. We did play around with the weighting of the factors for our 2015 AB8 analysis, but this is a tunable parameter. So when you look at, or if you download CHIT and you look at it and you want to play around with it yourself, each of these factors, their weightings, relative weightings, can be set by the user. But these are the default values we utilize in our estimate. So it's essentially it's coverage times the market, and your existing and potential coverage factors are equally weighted. The market is a little more heavily weighted towards finances than green vehicles and then education, and those 3 financial indicators are essentially equally weighted with each other. Any questions online? No? Okay, so after all that, this is essentially the culmination of all those data inputs that we had developed. Now we have this heat map, and you can look at the heat map and you can pretty generally tell, where the hot spots, San Francisco, Berkeley area, LA. But we did want to provide some kind of structured way to analyze this map and be able to identify the highest scoring areas and identify the areas that essentially have the highest need. So this was essentially a generalization and statistical analysis. It required 3 steps. So first you look for the highest ranking areas throughout the entire state. You then try to find the hot spots throughout the state. This is slightly different because the hot spots is a statistical analysis, and it essentially says that it finds the areas where locally you have a higher score than the areas surrounding. And then you merge those solutions. And then you essentially come up with, these are the priority areas that if you read it through the ABA report or went to the webinar or workshop with the CEC, these are the priority areas that we discussed, and this is the process to identify them. So when we looked at the full range of heat values across the state, the range was actually 0 to only 0.54. So essentially there's no perfect area in the state. It's not necessarily a surprising result, but just to keep in mind. Additionally, the distribution of those coverage gap values was heavily weighted towards the lower end. You can see clearly from this map, there's a lot of blue, essentially, right? A lot of deep blue that's a very low value. There are a few high-scoring areas that are much higher than the low and mid-scoring areas. So essentially, when you look at the data, it's a bit logarithmically distributed. So we utilize that to transform the data and generalize what are the highest ranking regions. So essentially what we do is we rescaled to that logarithmic scale. The user can define how many bins they want to classify all the values in. So you want to look for the top 20% on that scale, the top 40 or top 30%, etc. And you choose all the coverage gap values within that highest bin, and you essentially turn those into features that give you a draft of where the highest values are across the state. So we utilized in our ABA 2015 report 5 different classes. So essentially we're looking for the top 20% of areas in the state. And that looks like this. So you can see some of these areas look a little bit similar to what our final priority areas were, but they're not quite the same, and that's because this is only the first step. Second step is to really just run ArcGIS's built-in hotspot analysis. This is a pretty sophisticated statistical analysis that essentially, just because you have one hotspot, one area that has really high value, there might be areas around it that have a slightly lower value that could still be part of that overall hotspot. You don't want to essentially, you don't want to eliminate areas that are pretty high just because they're not the highest as well on a local scale. So what we do is we perform this local scale analysis as well, and we get a similar result to our previous one, and we merge the two. Now, for this year's analysis, essentially, the hotspot analysis created very similar areas to just the overall general highest scoring area analysis, the priority analysis, but they were larger, and so your final union of the two is a lot more like the hotspot analysis than the priority analysis. But that may not be generally true, so we still provided both tools for the future. And then after that, we do provide tools for doing some hand filtering throughout the entire process. Up to this point, we didn't really interfere with the process, with the calculations. We let the whole process happen, calculate what it would. But then at the end, we said, okay, it's probably not very realistic to try to say a priority area is very small, right? So we at least filtered out all the areas less than 1.5 square miles. That worked for our analysis this year, but that's, again, a tunable parameter that can be explored. And so you get out of this full analysis these priority areas. And so the whole point of the hotspot analysis was to say that, you have, for example, in this region, all these really bright yellow and orange, but they're really not that different from the green. These green areas should also be included in the priority area representation, especially when they're between two yellow areas. So that hotspot analysis ensures that you don't eliminate these regions just because they're a little bit lower, strictly below some threshold value. It generalizes the solution, essentially. Are there any questions in the room or online about that?
So the idea is that there's no station yet, but you think it's needed that we build it and then you think, oh,
so the question was essentially the idea is there's no station yet, but you build a new station, then people will go buy the hydrogen vehicle. So pretty close, but this actually also takes into account that there may be a station there, but there's still more demand than that station alone can provide, right? There might be a bigger market than that one station allows you to meet. So it's both that and also kind of an assessment of, the market is so big in this area, and even with 5 stations, we're not yet quite meeting it. And so you still need, that need is still going to be there for a 6th station, for example.
Mike Nichols, UCF. So are you implying that you have a way to put in capacity constraints for an individual station? You're saying 5 stations could do it or not?
So this is really a coverage analysis to this point, yeah. We're about to get into assigning capacity, but it's not in a feedback like you're mentioning. It's a post kind of analysis, yeah.
Jim, use that microphone. Thank you. Jim McKinney here. So I really appreciate all the efforts of ARB to use publicly available data in your model and in this discussion. And I'm curious if there are any automakers, here, I know we've got Lance here, I don't know if there are others who are on the phone, who have kind of compared this to their own kind of private, customer, data sets or their own projections on where customers might emerge for the initial launch. And just, if you think this is, pretty much right, is ARB really kind of pretty much got it right, or there's some discrepancies or modifications or suggestions?
Is there anybody raising their hand on the?
Okay. Not trying to single you out.
Is anybody raising their hand on the?
Yeah, not on here yet.
I will say, yeah. I can't speak for the OEMs, but I will say that earlier this year, the OEMs through the partnership did release a list of their priority areas, and it's they use a totally different basis, totally different analysis. Their suggestions are more finely tuned than ours, I would say. Like they would have, for example, in this Orange County area, they might have more specific neighborhoods that they put on their list. But when we compared our list with theirs, our priority areas do include essentially everything they do that we could have modeled. So they do include destination and connector stations, and that's outside the scope of this model. So yes, we did capture their station areas that they mentioned, but again, I can't speak for the OEMs, only my analysis of their letter.
So Phil Kazel from Energy Commission, can you just briefly go over again what the meaning of the red line is and whether that is significant in an area that would be funded or not funded or score higher or lower?
So the origin of this red line, this red line is the boundary of what we call the priority area in the AB8 report. That's the origin of the red line. It's to be able to communicate to CEC through our reports. What do we mean when we say you need to have stations in San Francisco? You need to have stations in San Francisco. That's the highest priority. Where in San Francisco do we actually see that count as? San Francisco might, and this might be, there might be a more common, perception of what San Francisco means, but maybe in other areas, what does it mean for Fremont? How much of Fremont? How much of San Jose? Where in San Jose? Where in LA is the highest score? Where, for example. So the red line is the outline of the analysis of where the priority areas are, and those red lines, those shapes correlate to the entries in the table. I forget the number from the AB8 report, but the table that shows you, priority area 1 is, for example, San Francisco. Priority area 2 is Berkeley, Berkeley, etc. Now, in terms of the solicitation, it's not going to be required that you are actually within these boundaries. We provided that still as a means to kind of direct everybody towards, hey, this is where we see the highest need. As you can see from this, slide, there is a value associated with literally every square mile of the state. So there's no bonus for being inside of a priority area. However, if you gravitate towards the priority areas, that would mean that in this analysis, you're gravitating towards an area that has a likely chance to have a higher location value. Natasha?
Could you go back to the San Francisco map? And tell me about the red line. So it looks like there's very red along the water in the upper right, and thin red along the water all of the west. Is there, or is that just a boundary?
You're talking about those lines right there? It's just thick right there because there are very small features. That's the outline of the waterway. It's just there's a lot more jutting out portions, and they're close together on the zoom.
So it's not hotter in the Embarcadero?
Not, well, the hottest portion is this entire, are you talking about this red shaded region, or are you talking about the red line?
So I'm asking, so the third part is it looks like there's a jaggedy red line that looks more like a boundary in the southern portion, but the others look so much thicker. Is there a value to the thickness of the line?
No, the line is, it's just the line. It's just that there's more features that are closely spaced, and so it looks like you have a thicker line. That's just the outline of the boundary.
That's where all the piers are.
Yeah, that's where all the piers are, yeah. That's not, so the shading inside of that boundary is the score, or the value.
Okay.
Yeah, maybe I didn't choose the right color. Maybe I shouldn't have maybe I shouldn't have chosen red for the outline. I thought it would stand out more, but yeah.
Jim and Kenny, so I'd like to follow up on Phil's question. So earlier, Andrew, you were really saying this is all on a kind of a continuum. There are no binary, good, bad, yes, no. And so I think just so we're all really clear, so this red line does not exclude anything that might be, say, in a green zone or a yellow zone.
Absolutely, yes. Okay. All right, so capacity. We've had a lot of questions about capacity and how we determine what is needed in the market. So we determine the capacity needs according to what we assess as the likely distribution of vehicles in the full early adopter market. We do this accounting for the existing station's capacity. So we can calculate, again, we can calculate just the market. We don't have to calculate the coverage gap, just the market itself. And we can say that when a station provides 6-minute drive time to some portion of that market, then that station is providing service to that portion of the market. It's a super fine detail. I'm not going to spend too much time talking about this, but actually assigning stations capacities to market areas is more complex than it sounds in ArcGIS, simply because of relationships that it chooses to allow you to choose between for what counts as overlaying or not. So this feature is, in our CHIT tool, this is the determine station 6-factor match, because it took quite a number of steps to do that, but it's all programmed in there. So if you look at that model later on, and you see it's giant, don't be too concerned. It's just trying to address some of the intricacies and little nuances of ArcGIS. So essentially what we do is we first identify what is the full adopter market. And we do that by doing that whole analysis that we talked about, except we don't include coverage from the existing stations. So essentially that will give you what is your full early adopter market. Then we do the whole process again with those existing stations, so we can separate out our priority areas. Because at the end of the day, what we want to do is we want to figure out how much capacity, new capacity, needs to be in those priority areas that we're saying you need new stations in. And then essentially, and then you account for all the stations that do exist that cover any of those areas, and then you assign vehicles to both those full market and those priority areas. And what we did is we utilized our chat tool that we have in-house, and we assigned vehicles according to a weighted sum of the market and the population within that area. And so what we do is we take the projection for the vehicle count, and we take that existing capacity. We make assumptions for how many for VMT in the year according to MFAC. We make assumptions, simple assumptions for how many kilograms are utilized in a day on average by any vehicle, and then we determine what is the hydrogen need or surplus in those areas. So for the pond concept, we analyze the 2021 need based on 34,300 vehicles. So you may have seen this slide or this table in the pond concept that says that the total capacity need in San Francisco for those 34,000 vehicles we project to be about 2,000 kilograms per day. Now that's looking out over a very long period of time. We have, from our own analysis with chat, all the vehicle projections for the intervening years from 2015 to 2021. And so we looked at those, and so we could figure out how many stations you're going to need in each of those years. And then we looked out over a shorter horizon, 3 to 4 years, to determine how many stations we reported are needed in the AB8 report. So essentially what we did was we said, okay, over the next 3 to 4 years, each of these areas has a capacity need. And if we assume that stations maintain an average over the next 3 years of 180 kilograms per day, that means that you're going to need, at least for capacity terms, this number of stations. So our number of stations is based simply on capacity, whereas the prioritization and the identification of where they need to go is based on the coverage, or based on the coverage in the market.
All right. So I see a capacity by region. So it's you're not trying to say capacity at each site. You're just saying in this region we have this many customers. Okay.
Yeah, totally. Yeah, you do not need 2,070 kilograms at every station in San Francisco.
Right.
Yeah.
I just want to make sure that. I mean, do you have individual estimates, or do you go finer grains?
No.
Measurement, or?
No, because we're just trying to do this. Yeah. So part of the other, I guess, one of the other motivating factors here is, I mean, this is all within, again, the scope of AB8, and we, it may be interesting for us to optimize or say, okay, the best station would be this station with these this capacity at this intersection, but in reality, that's really more up to the bidders in terms of what they see and what they want to bid on and what they want to provide. So.
But you have a gaps analysis, though.
We do. Yeah. Right. So we have a gap analysis, but the intent is to still be general. It's to provide general direction where it needs to go, not a gap analysis to give an optimal about, right? So. Yeah. Okay, and that actually covers all of what we did for the AB8 report, the development of the tool, essentially how it might be utilized in the upcoming pond. So the last two points I have here on the agenda are open discussion. One related to potential future development. Where do you see that we might want to go with this tool? What are the improvements? As I mentioned at the beginning, I realized it's a lot to digest, so this might be something that you can get back to us about, but if there's comments today, we definitely are opening the floor for that. So just to give some alignment for that, we have actually considered a few things. So we did talk about traffic volume. Mike Nicholas actually provided us with some suggestions to pursue there, so thank you for that. That's definitely one of the things that we were looking for additional information. We've heard oftentimes that maybe gasoline stations, or looking at gasoline station throughput, might be an indicator of the market viability for a hydrogen station. That's where people are refueling, so maybe refueling right now, so maybe if a hydrogen station is there, they might refuel there as well. And of course, the current funding paradigm is to co-locate at existing stations predominantly. It's open for greenfield, but predominantly we get those applications. So that data does exist, and it can be obtained by ARB, but so far, as we understand it, there are concerns of confidentiality of throughput data being published for the public view. And so since CHIT is meant to be a public tool, we might be able to find ways to aggregate and incorporate that data in a form that wouldn't compromise any businesses' confidential information. But right now, we have not pursued that yet. Origin destination studies, again, today and in the past, we've heard a lot of valid arguments about how this can actually be a different paradigm that might be more suited to the question that's trying to be answered. But again, we didn't find information prior to this that would work in our tool. We've heard today, though, that some suggestions for that. So again, any suggestions for origin destination data are definitely welcome. Hydrogen production facilities, we've considered whether or not, if you want to start thinking about the entire supply chain of hydrogen, how important would that be? Looking at the centralized production facilities, it could be a factor. It might move it more towards an optimization tool, so we weren't really clear about the importance right now. But if there's strong feelings about that, we're open to hearing that. Disadvantaged communities, environmental justice, other socio-political considerations. The state does have a number of goals and programs related to environmental justice. Pretty easily, some of these can actually be introduced into the calculations, or at least be compared to the output data from CHIT. In particular, we're looking at CalEnviroScreen as a possible rich resource for integrating these concerns. And then finally, the potential coverage factor I mentioned earlier. We only looked at a 6-minute drive time for that one. It could similarly be expanded to the multiple drive times that we looked at for existing coverage factor, but we did not have the time to develop that. So so what we would really like is some feedback, the appropriateness of these concepts, relative importance of these concepts, suggestions for data sets to explore, and then also other things that we have not identified. If there's a gap that we overlooked, if there's some other suggestion that you have to improve the concepts and the data, we're definitely open to hearing that. So I would actually open the floor to any suggestions online or in the room at this point.
There's nothing online at the moment.
Thank you. George took care of the key. No, Andrew, the most salient points to me or to us as an industrial gas supplier, some of the last things you just said right there. You know, where do you get all this hydrogen from? And particularly, you know, you got capacity models, and there's an existing infrastructure that's out there. A lot of that infrastructure to support hydrogen sales, most of it's captive to an on-site generator, to a refinery per se. That may be a source of a hub, so to speak. Then you got to look at, you know, the quality of gas coming off of such a hub, and then you got to look at the compression that you have available, or is it a liquid-based system? And you're going to look at the stations out there in all the grids and say, are they liquid-based, or, you know, what's the trend? Some of my competitors go with liquid-based systems, others go with delivered gas. Some go, but that delivered gas can be either transferred from the delivery vehicle on site to a ground mounted or a trailer mounted. Others, you're just going to leave the whole trailer there and take away the old one. So there's really three different things there. And, you know, so, and as you know, the hydrogen requirements are much higher pressure than the old industrial days. You know, 180 bar supply is pretty common for most tube trailers going down the road. So all those things are really factor in, particularly as for a ramp up. We're going to look at near term or medium term, or we're probably okay with mid-term. You know, where is the hydrogen coming from? You know, how's the infrastructure going to be in place to support all the stations, particularly in Northern California? Somehow, I guess you get data from, you know, I don't know if people thought how to go about that.
Okay.
That would be interesting. Thank you.
Thank you.
Got someone online. James, I've just unmuted you.
Okay, thank you. It's related to environmental justice. Maybe something that might be helpful for the near term is to determine locations that address not only the early adopter market, where people can afford these vehicles, but also adjacent areas that, you know, juxtaposition of areas that will also address environmental justice issues that are of great concern. Showing that maybe early on might be helpful, just not only technically, but just to show people that we're thinking of what the future holds.
Yeah, absolutely, and even at least as an analysis of how the results we obtained versus data that is out there on these environmental justice issues, and where these neighborhoods are located that have the most need. That's something we could probably pretty easily and pretty quickly develop. I know we've looked at similar already for the existing and funded stations in terms of how close are they, or what essentially what are the neighborhoods like in terms of Cal EnviroScreen for where these stations that are under construction or in place, how do they rank in that system? So I think we could do similar with this.
Yeah, exactly. I'm just encouraging sooner rather than later.
Okay, thank you.
Mike Nicholas, Davis. I think this is a really good, directionally relevant way to go. So, in all those things you mentioned, I would agree with. There's always little things you can change here and there, and you mentioned most of them. One question you did mention kind of the 6-minute drive time versus the other. I wasn't exactly clear on where it was used and where it wasn't used.
Okay.
Okay.
Yeah. So in the existing coverage, and I was discussing how we wanted to look at different drive times from different stations, how summing them up, right, in different areas. So for all the stations, we calculated their 1, 3, 6, 9, 12, and 15-minute drive times, and we associated essentially a coverage score for each of those. So that was when we did the existing station, when that whole discussion we had about, you know, how desirable is it there in terms of it actually already has coverage, right?
Right. So if it has coverage to someone who wanted it within 1 minute, that would be worth more than the one who
was like 6 minutes away, right?
Okay. And so where did you use the 6 minutes? Just the 6 minutes.
Yeah, just the 6 minutes was in the potential coverage, where we said, okay, conceptually you could put a station anywhere in the state, and then we said, okay, we were looking at just the block group centers, and then we said, how many people or how many households will you capture within 6 minutes of those areas, right? And so we could, you know,
you could have said 100% within 3 minutes, and then 50% within 4 minutes.
Right.
Right. Yeah.
Yeah, we could have done some kind of weighting like we did with the existing stations. The motivation for not doing it was simply that when you're trying to have ArcGIS compute, I forget how many, I think it's like 18,000 block groups, computing just 18,000 service areas took enough time. Right. So it's something we probably could do. We just didn't have the time to do it before. So and I don't know how much effect it really will have. It might have like a bigger effect than I'm anticipating, but it seems like one of those tweaks in the weeds that maybe we can investigate for future development.
And one last question.
Yeah.
So maybe not last, but so you're assuming a market here. Like what overall market you were expecting, and how does that relate to the price of fuel and the price of cars? Because it's going to go up or down in as far as capacity. If it's not, I mean, is it a priori you say it's going to follow some ZEV trend, or like is there any feedback with technologies, these sort of things?
So when you asked what do we anticipate as the you didn't hear the market, essentially the size, like how many vehicles?
Yeah, and how does that depend on
right.
price of fuel, price of gas?
So
all those things that actually do affect the market.
Right. So CHIT, it does not do the estimation of the size. It's relatively, this area has it's probably going to have a bigger market than that one. We get the size from chat, where we said, okay.
Got it. Yeah. Okay.
Yeah.
So Jim McKinney. So again, Andrew's a very, very strong presentation, and I think a really valuable tool for all of us here. So thank you for your work on this. So I kind of wanted to go back to Mike, and I know we've got Brendan here also from UCI. So I always get nervous when numbers kind of take on a sacred quality, like in the the roadmap report, 68 was the magic number. Now it's 100 stations is the magic number. So I get nervous around the number 6 if that's a magic number. And so one of the kind of ongoing discussions we've had in the fuel cell partnership working group meetings is, how likely are fuel cell electric vehicle drivers willing to kind of adopt new behaviors, new learnings the way EV drivers do, or how really wedded are they to the traditional gasoline IC engine view of the world? And I don't know if the academics or automakers here have an opinion on that, but I'm really curious about what the future research when we get into driver behavior, because this also ties back to maybe not having stations just prioritized in neighborhoods or where people live, but getting onto thoroughfares or maybe outside of a kind of a traditional route for somebody with an ICE. But I'm really curious, and comments again from the academics or the automakers here on that topic.
Hey, go ahead, Brendan. Go ahead. So I would say you can actually fairly easily just take some of the tools we've developed. So you've got the market tools, so where do the people live, and you can take some of that. We did a fast charging tool that actually CEC funded us to develop, and you can see based on the Caltrans household travel survey, you say how many people live in a county and go to other counties where they might actually go beyond the range of their vehicle. So it's actually not too many. It's like 5% of EMT in the state, and like 1 or 1.5% of trips that would need something like this. So, but you can actually prioritize where on I-5 people would run out based on their origin and their destination, and go around like that. So you can just use it. That's one idea. And then there's also we're running the EVMT project, which ARB and CEC are also helping fund, and we have a lot of data for a year to see, okay, on a household level, how many times does a household need to go, and where they live, and so we've got trips to Arizona and Reno, even farther, different states, but a picture of, okay, 1 year, where do people, and how often do they go? So.
Yeah, and I think one of the key issues in that study is that that study is also going to look at choices in households that can choose an EV versus a gasoline vehicle, right?
Right. Yeah. So that choice is actually, for this discussion, maybe it's not as germane, but it's more like on a household level, how many times do people actually go to the farm? Right. And I think But I mean, I guess I would ask you then, do you think if that might get to Jim's point as far as trying to determine how far are people willing to change their fueling behavior based on the vehicles? Yeah, and I think actually we're also going to get into that because for 12 months we'll have every gasoline refueling location per household. So that would be interesting to see like the distribution of where people refuel every year, and do they need 50 stations or do they need 3 over an entire year? So that, there's things we can look at there, distances, things like that to kind of get at that question. Yeah, I was going to say something else, but once we have those kind of detailed data, we can compare that to Caltrans and see how valid the stuff that we've already developed is. So there's lots of different ways to get at the value of long distance stations, and also surveys. Yeah.
So I think the GIS is really small sample size. So the CHIT, California Household Travel Survey. So when we worked with it, you see like one trip out of the zip code. It's like, okay, what's that really telling you? The other thing is, I think, Jim, what you were talking about is we have an early adopter market, right? And then out of that market where the people live, they have certain routes that they travel. And how well is that reflected in the travel survey?
That's more of it.
I think the long distance in the trip, maybe better in the CHIT to the DC fast charging. But for, I think what Jim's referring to, kind of need to know how those early adopters are traveling. And if they're doing something different than the general population.
True.
Not to jump on the bandwagon, but that's essentially kind of what
yeah,
we had.
And that's actually, yeah, CHTS is a good place, but very small sample size. Right. And that's why we aggregated at the county level for saying how many people go from LA to San Francisco versus the zip code to the zip code.
Yeah.
Right.
I think what Jim talked about is like how many people are going 4 or 5 or something like
right.
that from
Yeah.
Irvine to San Ana.
Right. Yeah. Okay. Do we have any other questions online? Any other comments on possible directions for the tool? Okay. I do have one other open discussion, and that is public distribution of the tool and of the results. So, of course, one of our principles is utilizing data that we can share. We provided summary results and our own assessment of those results in the June AB8 report, and we'll continue to do so. But further sharing of the tool requires essentially 2 things. One, to be able to share, essentially, ideally, an interactive map of that heat map so that interested stakeholders can look at ARB's assessment, ARB's implementation of the tool, the assumptions we made, what the result of all that is, and be able to look at just what is the result in a very specific area that stakeholders are interested in. Additionally, we want to be able to actually share the tool itself, share the model itself as a prepackaged download with a user manual and all of that, so that stakeholders can use the tool, maybe play with it if they want. There's a couple of questions that we do need to have answered. We're working on this actually as of this week, but currently ARB does not have the capability to host interactive online web pages. It's just not supported by our information services. So one of the potential solutions is to essentially create a web page where you could click on a portion of the state. There's just one image of the state, and depending on where you click, it'll bring up a high-resolution PDF. That might take us a while to generate, but it technically could be done. It's been done for other programs in other agencies for the state. So that's one potential solution, at least until and if we can get an interactive map available online. But we are working on that. We're trying to get that in place. Additionally, ArcGIS is not free software. You can actually, Michael Nicholas informed me this afternoon that actually you can get a free 1-month trial of ArcGIS just by supplying an email address. So you could pursue that, but for long-term use, it's not free software. Open source options do exist, but they're not supported by our information services, and we would have to essentially redevelop the entire tool in another program that would take a significant amount of time and isn't necessarily guaranteed to provide the same results or the same capabilities. So, downside of ArcGIS is it does cost money. The upside is we were able to develop the tool in the first place. So some of the open questions we have, how important is an interactive online mapping application to the stakeholders for being able to look at the analysis that ARB performed for the 2015 AB8 report? Is a solution that we propose to kind of click on a part of the state and you get a small PDF, is that sufficient for maybe at least for a stopgap in the intermediate time? How interested is everybody in actually having the ArcGIS toolbox that is CHIT, that you can actually run it, you could recreate ARB's AB8 analysis, or you could modify it with your own data or your own assumptions? How interested is everybody? Is that actually something we should pursue? Is the cost of ArcGIS a significant barrier for stakeholders to be able to make the most out of that download? And is there anything else that we're glossing over or we're not considering yet? So,
did you say the cost of it?
$2,500 is about.
Well, it depends on what level.
Yeah,
depends on ArcGIS is. I think it's like 10,000. But the basic is $2,500, I think.
Yeah.
For like private organizations, and then each module costs more. So I would.
Yeah, I don't know necessarily. ArcGIS I wasn't involved in procurement of ArcGIS. So.
No, it's used all over the world. Yeah, it's a big company. It's like the industry standard for geographic.
Actually, the company that makes it has an office in Midtown. Yeah, yeah, you can analyze anywhere in the world. It's a flexible platform. Is there any comments online on that?
No comments.
Okay. All right. So, oh yeah, Kasha.
From the California Energy Commission. So as you were speaking earlier, I was imagining that a person would have to use the map, get into a PDF to be able to share it with their coworkers and deal with it, because the moment you go away from the software, the thing you had just zoomed in on would go away, right? If it was interactive and on your website. So I think PDF is an excellent solution for the first year.
So if we had an interactive map, essentially, you know how you look on Google Maps and you zoom in on an area? Essentially what we would have is we would have just a layer. Think of it as a layer on top that is this entire heat map. And you could zoom into, for example, into the San Francisco region, and you might be able to click on this point here, say that's where your station is, or type in the address of the station that you're looking to propose, and then it would return to you what is the value at that point. What does this yellow mean? Give you a number for that yellow or that red, you know. And so it would be an interactive way for stakeholders to be able to kind of look at the analysis that we performed and look at what we're suggesting and see how, especially for potential applicants, see how their potential stations might be viewed or be valued in the eventual scoring process for an application. Just to give them a sense of how be open about the scoring process.
I'm speaking in support of
a number of PDFs, and if someone needs to dive deeper, they will. But detailed PDFs sounds like a great solution.
Okay.
You can also, share CANV files with Google Earth. That's kind of pretty easy for sharing files with people that don't have ArcGIS.
Okay. Yeah.
And you can look, you just have that layer and zoom in and out.
Right. Yeah. Thank you.
If you're planning to, because I think did you say that you would allow download of like shapefiles at all?
Yeah, that's what we're that's what we're planning. Yeah. Essentially, when you what we're planning for actually for the distribution of CHIT is that it will come with all the input and all the output files that would be generated during the run that we did for the 2015 report. So yeah, I'll have to ask our OIS on whether or not that's an allowed method, an allowed avenue. But thank you. All right. So if there are further questions, I'll be here for another half hour. Or if you have questions and you're thinking about all the information that's covered today, you have suggestions, questions, ideas, you want to get in contact, my contact information is on here. So I'm definitely open. Feel free to give me a call or send me an email, and we'll be in touch. All right, so if there's no more questions, I think we're done.
All right. Thank you.
Thank you, everybody.